Okay, great. Good morning, everyone. Hope you enjoyed last night. And today I will be presenting this study we conducted at OIT in collaboration with the International Council on Clean Transportation to assess the electrofuel supply potential in the US using PyPSA-Earth. So yeah, I'll briefly introduce you to the motivation and objectives of this work, then show you the methodology, how we modified, how we customized PyPSA-Earth to be suited to this study, and then I'll go through a few results of the work concerning the electricity generation deployment and giving you an idea of the hydrogen and e-kerosene costs that we assessed through this methodology. So basically we started from three problems. So first of all, the barriers to the deployment of advanced biofuel production, the need to decarbonize an hard-to-abate sector like aviation and the current fuel crisis, and the opportunity that we identified is that e-kerosene could become a major player due to the falling renewable electricity costs and the policy incentives on CO2 capture in the US. And this study will then use PyPSA-Earth to understand the impact of a large-scale adoption of e-kerosene and its impacts on the electricity sector, the hydrogen prices, and fuel costs, in particular e-kerosene. So we use PyPSA-Earth. As you may know, PyPSA-Earth co-optimizes investments and dispatch through system-wide cost minimization. And as a general setup, we use a model with a 100 nodes resolution and 3 hours temporal resolution. We conducted a myopic optimization in three different planning horizons, so 2030, 2035, and 2040, and I will show you the results for 2040 today, as there's no time to go through all of them. And we played with the model, customizing, for instance, the implementation of electricity demand. So we added matching of the distribution of electricity demand across the US according to the IA statistics, and provided future projections on the total electricity load based on the NREL electrification future studies. Also, we have a full sectoral coverage in the model, so we use the sector-coupled version of the model, not just the power sector model, because of the interactions with the hydrogen and e-fuel sectors. And we have a specially detailed modeling of steel, cement, and chemical sector, in particular considering ammonia and ethanol, that are used as CO2 point sources for e-fuels production. We used a specific version of the PyPSA technology data repository for techno-economic characterization of the technologies in the model, and it's freely accessible. We have now this US-specific techno-economic data source with using data from the NREL, from the ICCT studies, and so on, and National Petroleum Council for CO2 capture. And all the scenarios that I will show you later are sharing the same cost assumptions, while we also have different trajectories for costs in the US, considering different cost scenarios. Also, we applied tax credits as marginal cost reductions for 10, 12 years, depending on the different regulations that are now adopted in the US. And these tax credits are going up to $18 per megawatt hours for electricity generation, in particular for nuclear and renewables, and to 54 through $76 per ton of CO2 for point source CO2 capture, depending again on the scenario, because we have two different kinds of scenarios. One with high climate ambition based on the IRA 2022 tax credits, and the reference scenarios that I will show are using instead lower values that were modified with the introduction of the One Big Beautiful Bill. Okay, going on with the constraints that we implemented, so basically the customization that we made to the PyPSA-Earth code that we also contributed upstream. We have constraints for hydrogen production, in particular regarding the 45V pillars. 45V is a regulation assigning tax credits to eligible hydrogen producers. So we have hourly matching and deliverability enforced for hydrogen production through electrolysis, meaning that electrolysis must be covered by renewables production renewable production that happens within the same hour in the same grid region as the hydrogen production. And additionality considers that the electricity must come from facilities that are installed maximum 3 years before the hydrogen production takes place. These constraints are applied in two scenarios that I will show you later, so a reference scenario with 45V pillars and one high climate ambition scenario. And also these scenarios are sharing an imposed 8% e-kerosene blending rate in 2040 with a growing trajectory starting from 2030. And they, again, differ for the degree of climate ambition. Indeed, I'm showing on my right-hand side the constraints that we implemented on electricity generation. So we have a growing demand by 30 or 40%, depending on the degree of climate ambition, either no new transmission expansion or DOE projections for the two scenarios. And then currently stated state policies in the US for clean electricity generation, what can be both renewable or clean, including also nuclear, or 90% green electricity by 2040 in the high climate ambition scenario. Of course, these constraints are strongly shaping our results, and I will now go quickly through them. So concerning the electricity sector deployment and economics, we found out that in the regions with the highest renewable concentration, so it should be the Great Plains, the Midwest, and Texas, we also have the lowest regional LCOE with a range spanning between 40, more or less 40, and $50 per megawatt hour in 2040. And also the dispatch looks quite different across the two different kinds of scenarios. So in the reference scenarios, there's basically a sort of business as usual result with gas being the major electricity producer in 2040 again, even though renewables have quite a good deployment. While in the high climate ambition scenario, we have a huge increase in electricity generation from renewables, which is also pushed by the application of more extended tax credits, and solar and wind basically reach almost 80% of the generation, but also with a lot of curtailment. And going to the results about the hydrogen and e-kerosene costs, we have that there's a interesting effect by either having or not the application of the 45V pillars. So basically removing the 45V constraints, so hourly matching and deliverability and additionality in the reference scenario, we have that the only effect is basically a different distribution of hydrogen production, because it can happen also including fossil sources, and then basically it happens completely in the region where electricity costs are the lowest ones. That means the Plains region with 2.8 megaton of hydrogen produced in 2040 in the reference scenario with 45V pillars, while when removing the pillars, in particular hourly matching, produces this effect, the production is completely shifted to the Plains regions, and it produces almost 100% of the hydrogen that we have in this scenario that is just needed to satisfy the 8% e-kerosene blending rate. So we got 4 megatons of CO2 corresponding to 96% of total production. And here the e-kerosene costs are assessed at around $8 per gallon in the Plains region, while you can see from the color code in the map how the hydrogen cost is definitely quite higher than in the high climate ambition scenario, as it's quite obvious by the colors, but it's around $3 per kilogram of hydrogen. And here again, there is no effect from the tax credits assigned to hydrogen production, maybe because of the way we modeled tax credits. But yeah, in the bottom picture, in the high climate ambition scenario, you can see how the combined effect of tax credits and higher renewable share, much higher renewable share, bring costs to around $2 per kilogram of hydrogen. consider that, again, the tax credits for hydrogen production are around $3 per kilogram, so they have a huge effect here. And yeah, basically strong clean electricity mandates, the 90% clean electricity generation by 2040 mandate, lowers hydrogen costs in the main production hubs, which are, again, the same as in the scenarios above, so again, Great Plains mainly. And basically, the the kerosene cost falls to $5 per gallon. So it's almost, let's say, 40% reduction. And going to the conclusions of this work, so basically we started considering how e-kerosene could play a major role in the decarbonization of the aviation sector, but also its deployment strongly depends on the deployment of clean electricity generation and in particular on clean hydrogen costs and availability. So we use PyPSA-Earth to customize it mainly and adapting it to the US case. And we used it for an integrated assessment of electricity, hydrogen, and e-fuels, particular e-kerosene production under different policy assumptions in the US. And we found out strong clean electricity deployment is substantially lowering hydrogen and e-kerosene costs with a huge effect from this, while removing the 45V constraints, so allowing basically hydrogen production through electricity generated also with fossil fuels, mainly changes the spatial concentration of the production in the US, but poorly affects the costs. Thank you for the attention, and just a few announcements. So we have an OET-ICCT joint report with more detailed results and even more scenarios than the ones I showed you today. And also we're working on the deployment of PyPSA-NorthAmerica as a PyPSA-Earth fork. So we're starting from this US model with this customization that we made to improve basically the demand distribution and the representation of the hydrogen sector in the US. We'll expand it to Canada and Mexico, hopefully in the upcoming months. And also you can check out the GitHub repository of the project. We'll have soon a release, but it's already public, so you can already go through that. Thank you again.
Thank you for the presentation. How do you consider the exchange with Canada in the US-centric model?
Yeah, basically in the representation of the network that we have, the main connection to Canada and Mexico are also represented. So, the only problem with this is that basically since we are applying these 45V pillars in most of the scenarios, there is no basically there is no exchange in the regions where, with Canada or Mexico, in the regions where hydrogen production is taking place, because the electricity must be produced where it's used. So yeah, the representation of the connections with Canada and Mexico are there, but in this particular case, they are having no effect in the scenarios where the 45V pillars are applied.
So are you using the flows of today and it's the same flow all the way to 2040, 2050, or do you accept that these lines increase?
Yeah, we have an expansion of the transmission line, but it's controlled and it's based on the DOE projections, so both for national development and for international, let's say,
Okay, so you use the DOE projection.
Yeah, we use the DOE
projections
projections for the scenarios where there is a strong deployment of renewables, where we're considering no new transmission expansion in those scenarios where we're not considering a high degree of climate ambition. And we had to use the DOE projections because since we're using a cost optimization approach and we're also giving strong incentives to hydrogen production through the tax credits, we were getting basically an explosion of the installation of the expansion of new transmission lines. So we had to sort of reduce this effect through user constraints.
Okay, thank you.
Thank you.
Thank you so much for your presentation. My question is mainly about the hydrogen parts. Just wondering that because optimization problems, so the model select the low-cost electricity to generate hydrogen, correct? And then is there, just wanted to know, is there any hydrogen transport that considered? Or because, the great part of a hydrogen cost is related to hydrogen transport. And just wanted to know, how did you consider transmission distribution for hydrogen to produce e-kerosene?
Yeah, we're basically, in the model we have hydrogen pipelines characterized with their costs and also considering repurposing of existing gas infrastructure for hydrogen transmission. In this particular case, again, since basically those costs would hinder the transport to other regions, basically what we found out is that e-kerosene production is happening in the same regions as where hydrogen is produced. And then since we are considering zero or negligible transport costs for the produced e-kerosene, basically what we have is that hydrogen and e-kerosene are produced in the same region, and then the e-kerosene is transported at a negligible cost to the different hubs where it's going to be used. So different airports, so we have detailed modeling of aviation demand, and basically what we have is that if we want to implement some transport costs for e-kerosene, it would be easy to do, but that shouldn't have a huge effect on the results.
Thank you so much. And my second question, just curious to know what type of electrolyzer did you consider for this work?
So we consider both alkaline electrolyzers. We have 3 different kinds of alkaline electrolyzer technologies that are modeled, but just basically distinguished according to the size. And then we have the proton exchange membrane electrolyzer and SOEC. And we also have other hydrogen production technologies, but in this specific case, we are not considering them because the 45B pillars are mandating that hydrogen has to be produced through electrolysis.
Yeah, any reason not to consider PEM electrolyzer, especially for Rampon, Brampton, when they want to couple it with electricity grid is much, much better?
Yeah, we also have these constraints implemented in a simplified way, because otherwise the computational cost was increasing a lot, and let's see, we could have this sort of representation also for other technologies, but we prefer to, let's say, keep it simple, but mainly because the spatial scale was already quite extended and the model, let's say, was taking a lot to be solved.
Thank you.
Thank you.
Very quickly, I have the same question. So how do you constrain the flexibility of the electrolyzers?
Yes, again, yeah, we're considering it in a very simplified way. So we're just representing minimum utilization constraints, and we were also trying to implement some ramp-up features, but again, this was increasing the complexity of the model by quite a lot. Yeah, so we decided to keep it simple, but actually, the results with this simplification are not too different from the ones that we were getting with a more detailed implementation of flexibility.
I'll ask more questions later. I'd like to know details.
Thank you. Thank you again.